coming from. He's going to be giving our colloquium from the department. For those not from USC, on Fridays we run this colloquium series where we bring people, they talk in a broader sense to our community and introduce new areas to our grad students and our faculty. And for our faculty, Jeff is also part of our Big Ideas in Dynamics and Geometry workshop that we're running with Ben and Noel in the two corners, and it's going to happen also on the weekend in ARC. You're welcome to come, ARC 241. We're going to have more talks by our speakers and group sessions. So thanks, Jeff. You're going to talk about Affine Geometry and Auslander Conjecture. May start you to stop you after.
Okay. Sorry. Get rid of this thing here. Okay. Okay, thank you. Thank you so much to the colloquium organizers, in particular Laura, for inviting me. And thanks for the opportunity also to speak tomorrow at this very nice conference. I'll say that my talk today and my talk tomorrow are not very much related. So if you don't like this talk, you can still check out tomorrow's talk too. I'm going to talk about affine manifolds, which is a certain type of geometric structure that I think is very interesting and has a very, I think, tantalizing sort of history and set of open problems. But I want to start, before I get into that, with okay, hold on. Oh, no. What's going on here? What's that? Click the thing here. Click. Okay, click. There we go. I want to start with a quick overview of the subject of locally homogeneous geometric structures, which is sort of type of math where this story fits in. Okay, so let's start by defining the word geometry. How many people in this room do geometry of some sort or another? Yeah, everybody thinks they do geometry, right? No. I'm going to tell you for the next 50 minutes, geometry will mean this. So what is a geometry? It's a homogeneous geometry. It's a homogeneous space. It's a pair G comma X, where X is a manifold, and G is a Lie group acting transitively on X by diffeomorphisms. All right, so how are we meant to think about this? So X is the sort of space where we're going to do geometry. And what types of interesting sort of geometric features or notions are we going to study in X? Well, that's where G comes in. It's called the structure group or the symmetry group for the geometry. The local quantities or no. One example, just to say it, because you're probably all thinking it, is it could be that G is the isometry group of some homogeneous Riemannian metric on X. That's a perfectly good example. That's not the type of example we're going to be interested in. We're going to be interested in non-Riemannian GX geometries today. Okay, so what do you do with a geometry? Well, you try to build topological manifolds out of it. So this is a definition that goes back to Ehresmann and was popularized by Thurston as part of the geometrization program for three manifolds. So if you have a manifold M and a GX geometry, a GX structure on M is defined by taking an atlas of charts into X so that the transition functions are elements of G. So the picture you sort of draw when you first learn this stuff is you've got X over here. You've got your manifold M. Okay, here it is. Maybe it's some topology. And then you make local coordinates on M. So you take little patches of M, and you map them diffeomorphically into X. You cover M by these coordinate charts in such a way that when two coordinate charts overlap, the coordinate change function, the transition function, on the overlap is a locally constant element of our structure group. Okay. And the point is, remember, we're interested in G invariant local features in X. The point is that when you have a GX structure on M, any G invariant quantity you can measure here in X pulls back to be meaningful on M. So we endow M with interesting local structure inherited from X. Okay. Okay. Great. So the fundamental question in this topic is, or one fundamental question in this topic is about the topology of these manifolds. So if you have a GX geometry, which topological manifolds M admit a structure modeled on this geometry? So which topologies can you build by essentially taking chunks of X and gluing them together with elements of G? Okay. All right. Good. So a really nice example of a perfect answer to this question comes from the geometrization theorem in dimension 2. So here are the three homogeneous two-dimensional Riemannian geometries that you've probably seen sometime in your life: spherical, Euclidean, and hyperbolic. To hear that the space X is the two-sphere, the plane, or the hyperbolic plane. And the group G is the orthogonal group, the isometries of the sphere, the isometries of the plane, which are the rigid motions of the plane, or the isometries of the hyperbolic plane, which is this Lie group PGL2R. And in these geometries, of course, they're defined by the symmetry group, but just to say what it is, the interesting invariant local structure is, of course, given by a Riemannian metric of constant curvature, either positive, 0, or negative. Okay, who's played with these three geometries before at some point in their life? Okay, all right, good. Okay, so of course, we think about two manifolds, surfaces, and try to equip them with these three types of geometric structures. There's an incredibly clear answer as to which ones can be equipped with which. Every closed surface S admits a geometric structure modeled on exactly one of these three geometries, and the type is determined by the Euler characteristic I of S. Okay, if the Euler characteristic is positive, you can put a spherical structure on your surface. If it's 0, you can put a Euclidean structure. If it's negative, you can put a hyperbolic structure. Okay, so we've got geometry on the one hand, and topology on the other hand, the Euler characteristic. And there's a beautiful connection between the two. That's the type of answer we're looking for to our fundamental question. Does that make sense? Okay. Great. Oh yeah, I was supposed to say something else here. What was I going to say? Yeah, there's a geometrization theorem for three manifolds you've probably heard of, which also gives a beautiful connection between the topology of three manifolds and the types of geometric structures it can support. And that story, there's 8 homogeneous Riemannian geometries. But the picture is a little less clear to state, it's a little harder to state, so I won't state it here, but something like this happens in dimension 3 as well, but for Riemannian geometries, not again in higher dimension. Okay, all right, but the main object of today's talk is not a Riemannian geometric structure. As I said, it's something called a flat affine structure on a manifold. So let me give you 2 definitions. All right. So definition 1, an affine structure is just a GX structure on M, where GX is affine geometry. Namely, X is Euclidean space, R to the D. And G is the group of affine automorphisms of R to the D. So these are just, you guys have worked with these maps in calculus, right? They're just affine transformations of the form X maps to AX plus B. There A is just an invertible matrix, and B is a translation vector. Okay. So in other words, a GX structure is it's an atlas of coordinate charts in RD where the transition maps are actually just affine transformations. Okay, cool. All right, what does an affine structure on a manifold M give you? There's no invariant Riemannian metric, right? I mean, the dilation counts as an affine transformation. Affine transformations can skew and shear. So can anyone think of some invariant notion in RD that's invariant under affine transformations? Yes, Steve? Lines. Straight lines. Okay, very good. So affine transformations take straight lines to straight lines, right? So if I have a curve on my manifold and I have equipped it with an and I've equipped my manifold with an affine structure, I can make sense of the question, is this curve a straight line in my affine structure? How do I check? Well, I look in this chart. Oh, it looks straight in this chart. I look in this chart, it also looks straight here. If it looks straight in every chart, then it's a straight line. And the point is that because of this rule about my transition maps being affine transformations, if it looks straight here, it's going to look straight here too. Okay, so that's a well-defined notion. Okay, anything more specific than straight lines? What?
Parallel?
Yeah, parallel lines, yeah, parallel lines. True, you know, flat hyperplanes, right, things like this. Something else that makes sense, which is a little bit counterintuitive, is the notion of a straight line parameterized at constant speed. Right, you can parameterize at constant speed if you change that parameterization by some affine transformation, you get another line parameterized at constant speed. The speed is not meaningful, but constant speed is meaningful. So particularly the notion of, you know, a curve that is not accelerating is meaningful in this geometry. And that leads us to the second definition. I would say that the fundamental invariant structure of affine geometry is that of a flat connection, right? A flat connection on RD. So definition 2, an affine structure on a manifold M is a flat torsion-free connection on the tangent bundle. Okay, do we have any differential geometers here? Okay, so maybe you prefer, yeah, maybe you prefer this definition, but for the rest of you, maybe you don't. Maybe you prefer this one. These are the same though, and it's easy to go back and forth. That's a little exercise for anybody that's had the basic differential geometry. Okay. So what are some examples of affine structures? Well, example 0, a Euclidean structure on M is an affine structure. Why? In definition 1, our transition maps for a Euclidean structure lie in the isometries of R to the D. And every isometry of R to the D is in particular an affine map, right? Like rigid motions of Euclidean space are in particular affine transformations. Okay, so our structure group is strictly bigger. That means that every geometric structure modeled on this smaller subgeometry counts as an affine structure. Or in definition 2, if you like, you have a Euclidean metric on your manifold, you can take the Levi-Civita connection, and that's a flat torsion-free connection on the tangent. Okay, good. All right, so let's talk about affine structures on the torus as a nice example. I wouldn't be giving this talk if there weren't any non-Euclidean affine structures, right? So let's see what we have here. So here's 2 examples of an affine structure on the torus. So here I'm going to make an affine structure by taking the fundamental group of the torus, which is Z cross Z, and letting it act on affine space properly discontinuously. Those words make sense. Or, you know, even if they don't make sense, you look at this picture and you say, okay, this is a picture we've all seen before. It's a picture of the plane tiled by parallelograms. The way that the tiling is formed is by a lattice of translations, right? So if you take the quotient by the action here, you get what's topologically a torus, but it's in particular equipped with an affine structure that inherits from R2 here. Okay, but this is Euclidean, right? This counts as a Euclidean structure. These translations are actually Euclidean isometries, right? So that's not that interesting. A more interesting picture is this one. So here, again, we've tiled the plane by quadrilaterals in a Z cross Z action worth of ways here. But the action is not by translations, right? You see that the quadrilaterals seem to be kind of bending around. In fact, the affine transformations involved in this picture have non-trivial linear part. They're not just translations. They actually have some kind of non-Euclidean linear part as well. Okay, you take the quotient, you get topologically a torus endowed with a very different looking affine structure. All right. Does that make sense? The picture makes sense? Okay. These affine structures are both complete. There's also something called an incomplete affine structure, which is very interesting as well. Those don't come from a nice picture in R2. If you lift their affine structure to the universal cover and try to develop it by analytic continuation into R2, you would see a kind of messy picture like this. Those are very interesting, but we're not going to look at those at all today. So you can forget about that picture. So we're going to focus on complete affine structure. These are just to say it again, an affine structure on M is complete if it comes from a quotient RD mod gamma, much in the way these two did, where gamma is a discrete subgroup of the affine automorphism group whose action on RD is free and properly discontinuous. Okay, so free, what does free mean? What does a group action being free mean? No fixed points, right? Okay, so no fixed points. And properly discontinuous just means that all compact sets are sent off to infinity in the right way. But essentially, free and properly discontinuous together is exactly what you need for this quotient to be a well-defined Hausdorff manifold. So these are the actions with the correct dynamics to give us manifolds in the quotient. Okay. Great. All right, so great. So back to our fundamental question. We like affine geometry. We'd like to know which topological manifolds admit a structure modeled on affine geometry. So let's start with dimension 2. We know that a torus admits, and a Klein bottle admit a Euclidean structure, so in particular an affine structure. So it's natural to wonder, is there any other type of surface that could admit an affine structure? What about a hyperbolic surface, a surface of genus 2 or 3? Could that admit an affine structure? And the answer is no. If you have a closed surface S that admits an affine structure, its Euler characteristic is 0. So any surface that admits an affine structure already admits a Euclidean structure. We don't see any new topology by expanding our universe to affine geometry in dimension 2. I want to sketch a proof of this theorem because it's sort of instructive for some of the things that will come up later in the talk. I just want to talk about the complete case. So let's try to prove it. Suppose that S is the quotient R2 mod gamma, where gamma is some subgroup of the affine automorphism group acting freely and properly discontinuously in R2. This group gamma, as an abstract group, is just a copy of the fundamental group of our surface. Okay. Okay, so what we do now is we look at the linear part. So each affine transformation has a linear part, what I called capital A, and a translational part. So let's forget the translational part and just save that matrix. This is a homomorphism that projects to the linear part. And now we'll observe a very elementary but powerful lemma. The lemma is that the linear part of every element in gamma has to have 1 as an eigenvalue. This is a 2 by 2 matrix, and I'm claiming it has to have 1 as an eigenvalue. Okay? This is not deep, right? If I have an affine transformation, okay, x maps to ax plus b, and I know that my action is free, which someone told me a minute ago means no fixed points, then I should not be able to solve the fixed point equation for this transformation. Let's try. Fixed points. What's the fixed point equation? Ax plus b equals x. Okay, how do I solve this? Subtract x to the other side and factor a minus I x, put b on the other side is minus b. Okay, I can solve this equation by inverting a minus I. And then I would find a fixed point. So it must be that A minus I is not invertible. In other words, 1 is an eigenvalue of it. Okay. Haven't taught linear algebra in a while, but I think that's right. Okay, why is this a powerful observation? This is actually one of the kind of fundamental observations that leads to a lot of important things in this topic. Because 1 being an eigenvalue of a matrix is an algebraic condition. So this property passes to the Zariski closure of the group of linear parts of gamma. What's the Zariski closure? It's just the smallest Lie subgroup of GL2R containing the given group. Okay, so discrete subgroups of GL2R are quite complicated, but Lie subgroups of GL2R are not very complicated. Okay, and in particular, Lie subgroups of GL2R, where every single element has 1 as an eigenvalue, are really not complicated. They all live inside of a group that looks like this. Or what did I do? Or this, after conjugation, any Lie subgroup of GL2R with this 1 eigenvalue condition lives in one of these two-dimensional subgroups. Okay. And these are not very complicated Lie groups, right? These are semi-direct products. So what we observe by looking at these is that both of these subgroups are solvable. Okay. Who knows what solvable means? I don't regret asking this, but okay, good, most of you. So of course, the most basic thing a group can be is abelian, right? The next most basic thing maybe is solvable, right? It means that it's not quite abelian, but it's a abelian extension and an abelian extension and an abelian, etc. It's somehow made out of finitely many abelian groups in a reasonable way. Okay, good. So L of gamma by the lemma is contained in one of these. So it's solvable. But in fact, that's going to mean that gamma was solvable because, you know, the affine group is just a abelian extension of the general linear group. And so we found that gamma is solvable. So the fundamental group of our surface is solvable. And so in fact, our surface can't have negative Euler characteristic. Surfaces of negative Euler characteristic are hyperbolic. Their fundamental groups are word hyperbolic. They're very, very non-abelian. They're not solvable. So we know we couldn't have had a negative Euler characteristic here. And positive Euler characteristic is easy and different. Okay. Okay, so the point here that I want you to remember is this 1 eigenvalue condition, the freeness of our action here implies this 1 eigenvalue condition, which puts a big restriction about where the linear parts can live. Okay, that'll be a theme recurring. All right. Okay, going on. In general dimension D, we'd like to, you know, again, try to answer our fundamental question in higher dimensions as well. First, let me remind you of the theory for Euclidean manifolds. You guys are probably aware of this, but they're the very famous Bieberbach theorems for Euclidean manifolds. The first one says that a compact Euclidean manifold is finitely covered by a torus. Okay, so if you have a compact manifold in any dimension, and you can manage to put a Euclidean metric on it, it's essentially a torus. Like there's some interesting, finite cover stuff to look at, but it's essentially no more complicated than a torus. So in particular, it has Euler characteristic 0, and it contains inside of it a finite index subgroup, which is a copy of the fundamental group of the torus, just Z to the D. So up to finite index, the fundamental group of the Euclidean manifold is just Z to the D. It's the most boring possible group. What about for non-compact Euclidean manifolds? So let me say this in the language of group actions now. So suppose I have a subgroup gamma in the isometry group of Euclidean space, which acts freely and properly, well, doesn't need to act freely, but anyway, properly discontinuously on R to the D. Well, even then, even if the quotient is not compact, the this group gamma has inside of it a finite index subgroup isomorphic to z to the k for some k. Now k could be less than d. Okay, so again, this group is virtually just a copy of z to the k. Boring, right? You could say more, the quotient manifold, Rd mod gamma, is this non-compact Euclidean manifold. It's actually a flat orthogonal vector bundle over a compact Euclidean manifold. So it's somehow something that fibers in a nice way, and deformation retracts down onto something to a compact Euclidean manifold. So the point is the non-compact case is not much more complicated than the compact case. Okay. All right. All right. We'd like an analogous characterization of the topology of affine manifolds. We'd like a structure theorem like this that says you're an affine manifold, your fundamental group is this, and your Euler characteristic is this, and everything is simple. We'd like to know, does such a characterization exist? Okay, in dimension 2, the answer is the same. Let's go to dimension 3. I'll show you there's at least some affine manifolds which are not Euclidean. So in dimension 3, okay, yeah. I mean a vector bundle whose structured group is the orthogonal group. Yeah, don't worry about it. Just a vector bundle over a Euclidean manifold. Its fibers are vector spaces. Deformation retracts onto the bases. Yeah. Okay. So all right. So let's do this example. So here I'm going to make my example as the quotient of a lattice inside of a solvable Lie group. So here, take this Lie group G. It's parameterized by three variables. You see X and Y are kind of just free translations, but Z has this kind of exponential expansion and contraction tied in with it. So this is a subgroup of the affine automorphisms of R3 in a natural way. And it's not abelian, not virtually, it's not abelian, it's a semi-direct product of an R2 here. This is an R2 of translations together with R, the Z part. Okay, but the twisting there is non-trivial. What are these lines? Yeah. Okay. This is a 4x4 matrix, right? Yeah, so maybe you've seen this. Okay. Yeah, I'm sorry. I kind of hope people have seen this notation for affine transformation before. Let's just say this. This is the linear part of the affine transformation, and this is the translational part. If you let this act on all the vectors in R4 that have fourth component 1, it will not change the fourth component. So it'll preserve that affine subspace of R4. And so you'll see an affine action on a copy of R3 sitting at height 1 in R4. That's why the notation. Does that make sense? Anyway, yeah, this is the linear part. This is the translational part. Okay. Thank you for the questions, guys. Okay, but here inside of this group, here's a lattice. It's generated by 3 matrices. I claim it's a co-compact lattice inside of this solvable Lie group. It's a semi-direct product of Z squared with Z in a non-trivial way again. And G mod gamma is what's called a compact solve manifold. It's compact and it comes as the quotient from a subgroup of a solvable Lie group. Okay, but I already realized G inside of the affine automorphisms of R3. And I'll note, you can check this if you're bored, that the action of G on R3 in the way that we just talked about, right? Acting on the vectors A, B, C, 1. That action is simply transitive, okay? So in fact, this manifold is naturally an affine manifold. It's what's called an affine solve manifold. Okay. So it's an example that does not fall into the same category as Euclidean manifolds because it doesn't have virtually solvable fundamental group. Its fundamental group is non-trivially twisted. However, it's not that complicated, this manifold topologically. you can use the solvable structure of G to decompose this manifold into Euclidean pieces in a nice way. If you take the commutator subgroup of G, you just get the R2 of translations. If you take the commutator subgroup of gamma, you get the Z2 inside of there. And so the quotient of this by this is just a Euclidean torus. And in fact, the whole 3 manifold here fibers over the circle, which comes from taking the quotient by the commutator subgroup, sort of first factor in the derived series or whatever you say. So it fibers over the circle with fiber a torus. Okay, so this is a 3 manifold, which does not emit a Euclidean structure, but it fibers into Euclidean fibers over Euclidean base. Okay, so it's a tiny bit more complicated than a Euclidean manifold. Yeah. Yeah, it is a mapping. It's a map. It's a. What is the mapping class? I can't see it right now. It's probably something like 2111. I'm almost sure that's what I would have done here. So.
I see root 5 saying.
Is that root 5 should be involved? Okay.
Yeah, nice.
Yeah. It's an Anosov mapping torus. That's right. Yeah. Okay. Great. Let's go on. So that brings us finally to the conjecture named in the title. So it's called the Auslander conjecture. It goes back to the 60s. It says that if M is a compact, complete affine manifold, so a quotient of affine space by a group gamma, a compact quotient, the way we've been talking about, then actually that group gamma, or the fundamental group of M, contains a subgroup H of finite index, which is not abelian, but solvable. So slightly more complicated than abelian. So, or as we say, pi1 of M is virtually solvable. That algebra statement, which doesn't really suggest anything about the geometry directly, turns out to be equivalent to saying that M is finitely covered by an affine solved manifold. So in other words, the conjecture says that every complete compact affine manifold should be kind of like the example on the previous slide. It should be some sort of iterated fiber bundle structure, which you can read off from the solvable series of the fundamental group. It should fiber in Euclidean pieces over a base, which fibers in Euclidean pieces over a base, which fibers in Euclidean pieces, finitely many statements like that, down to a Euclidean base. Okay. Cool. I love this conjecture. This is one of my favorite problems in math. I don't know if it's true or false. I go back and forth. Sometimes, some days I think it's true, some days I think it's false. Let me tell you a little bit about the history of it. So it actually wasn't conjectured by Auslander. It was claimed by Auslander. He was trying to prove the complete case of Chern's conjecture. Chern's conjecture is another famous conjecture in this topic. It says that the Euler characteristic of any compact affine manifold should be 0. That's still not known in the incomplete case. That is known in the complete case due to later work of Constant and Sullivan. But Auslander was trying to prove that in the complete case. And the way he proved it, or tried to prove it, was by proving this much stronger statement. There was a mistake in his proof, but actually this statement is almost more interesting than Chern's conjecture. It's much stronger, right? It's a much stronger structure there. Okay. So it's known to be true up to dimension 6. That's due to work of Fried and Goldman in dimension 3, and Tomanov and Abels, Margulis, and Sleufer going up to dimension 6. And the way that they, particularly Abels and Margulis and Sleufer, analyze all the different possible Zariski closures with the one eigenvalue condition. So if you can assign yourself the problem, like try to do it in dimension 3. Okay, take the group GL3R. Try to find every Lie subgroup where every element has 1 as an eigenvalue. There aren't that many. I bet you could do it. Now try to do that in dimension 4. It's still tractable. Do it in 5. You can do it. The list grows though. In dimension 6, there's getting to be kind of a lot. And then in dimension 7, there starts to be a lot of cases to analyze, and some of those cases don't have any answer yet. So this one eigenvalue condition is very kind of important, especially in the sort of low dimensional cases of this theorem. All right. Great. So sorry, I think I wanted to say more thing. Okay, well, we're gonna spend the rest of the time talking about this conjecture. So okay, here it is again. If gamma, I'll say it in the group theory way, if gamma acts freely and properly discontinuously with compact quotient by affine transformations, then it's virtually solvable. Okay, and the word virtually solvable might remind some of you of the Tits alternative, right? So the Tits alternative applies here. This is a very strong dichotomy that happens in a lot of group theory situations. It works here. So in fact, gamma being virtually solvable, which means gamma is not very complicated in the way I've been trying to get across, is actually equivalent to the condition that gamma does not contain a non-abelian free group. Okay, so remember, solvable means sort of almost abelian. The non-abelian free group of rank 2, say, that's the least abelian group on the planet, right? You take 2 generators and you declare them to have no relations whatsoever. So there's no commuting happening at all there, right? So the Tits alternative is saying, okay, if you're not virtually solvable, then you must contain a free group of rank 2 or higher. Okay, so this suggests a good way to prove the Auslander conjecture, right? All we need to do is show that it's not possible for the free group of rank 2 to act freely and properly discontinuously by affine transformations on RD. That's all we got to do, right? Okay, unfortunately, that is not true. It turns out, and this I think was quite a surprise at the time, 40 years ago now, Margulis discovered the first examples of non-abelian free groups acting freely and properly discontinuously by affine transformations in dimension 3. The quotient affine manifolds are nowadays called Margulis spacetimes. They're called spacetimes because actually the action, it's more than just an affine action. It preserves a flat Lorentzian metric. Turns out it has to. If you did your homework about the Zariski closures in 3 dimensions, you'd find SO21 is the only interesting one to look at. Anyway, these exist. There are complete affine manifolds with free fundamental group. Why are these not counterexamples to the Auslander conjecture? So so gamma is not virtually solvable, but yeah, they're not compact, right? They're not compact. Indeed, a quotient of R3 by a free group cannot be compact on, homological dimension grounds. Okay, so these are non-compact complete affine manifolds with free fundamental group. So their existence shows that if the Auslander conjecture is true, there's some big difference between the way compact manifolds behave and non-compact manifolds behave in affine geometry. So, that's kind of a big difference than what happens compared to Euclidean geometry. All right, so Margulis discovered a few examples of these things. In the last 40 years, people have studied them, their geometry, topology, and deformation theory. Let me just write a few names here. And there's quite a lot of interesting math that has happened studying these Margulis spacetimes. A lot of my own work has focused on studying these things. So I just want to highlight a few results, which I'll try to do quickly. So it turns out that there was an open question about what the topology of these Margulis spacetimes is. And it turns out you can make them all out of polyhedral domains called crooked planes. So here are 4 crooked planes in R3. Try to rotate them around for you. I guess I could have just pulled up the Mathematica file and done this in real time. But these are 4 disjoint surfaces in R3, and if you know what this word means, you can play ping pong with these surfaces affinely. Okay, so you can make a free action, you can make a free group of rank 2 act by affine transformations by playing ping pong with these surfaces. It turns out you always get a proper action that way. We proved with Francois Gueretot and Fanny Castle that every Margulis spacetime, every properly discontinuous action by a free group in R3 actually admits a fundamental domain of this type. Okay, so in particular, the topology of the quotient is clear. All of these three manifolds are handle bodies. Okay. I'll just say this very quickly. We also studied the moduli space of all possible Margulis spacetimes. We showed that, you know, it's well known that to each Margulis spacetime is associated a non-compact hyperbolic surface. We showed that the Margulis spacetimes associated to a particular hyperbolic surface identifies with the arc complex of that surface in a neat way. Okay, so we can parameterize the entire moduli space in a nice way. Okay, and so this suggests a better strategy towards the Auslander conjecture than our first one. Again, to show the Auslander conjecture, you need to show that every co-compact free and properly discontinuous action by affine transformations does not contain any free group. So what we can do is we can just try to understand all proper affine actions by free groups, like all of them. Let's sort of catalog all of them and show that none of them, you know, they're all kind of weird and asymmetric, and there's no way they could fit together into a larger co-compact action. If we really understood all of them, maybe we could try to start to make an argument about why they don't fit inside of a co-compact action. That's kind of, I don't know how realistic that is, but that's a dream. Okay, so this suggests to study higher dimensional Margulis spacetimes. You know, not try to do what we've done in dimension 3 and in all dimensions. This is quite hard. So first of all, locating like the types of geometries where they can occur. In other words, what are the possible Zariski closures? That's already hard. I mentioned Abels, Margulis, and Seufer undertook this up to dimension 6. Ilya Smilga has some really nice work showing what's, you know, which representations of which Lie groups with the one eigenvalue property do admit proper affine deformations for free groups. And my student, Neja Zeger-Korenjak, has been studying recently maybe the beginnings of a construction that could start to parameterize one part of this moduli space. It's a construction called higher strip deformations, which is quite cool. Okay, but once you figure out where they can occur, you need to try to parameterize the moduli space. And everything we did in dimension 3 is very, very specific to a low dimensional coincidence of Lie groups that really makes the story entirely about hyperbolic surfaces. So I would say there's not a lot of hope at the moment to actually fully characterizing the moduli space of all higher Margulis spacetimes. Okay, so what should we do? Well, let's try to disprove the Auslander conjecture instead. Why don't we search for counterexamples? I'm not going to prove it this way. It seems too hard. Maybe we should try to do the opposite thing. Just go where the math leads us, right? So how would we do that? Well, we don't have any counterexamples, but maybe we can try to make examples which are somehow close to being counterexamples. So if I take a complete affine manifold, let's measure how non-compact it is. And one way to do that is the notion of virtual cohomological dimension. So the VCD of n is the largest dimension in which there's non-trivial cohomology in some finite coverage. Okay, so it's sort of measuring, if the manifold, let me say this, the VCD is between 1 and D, the dimension of the manifold, and the manifold is compact if and only if the VCD is D. Okay, so D means compact, 1 means really far from being compact, and somehow the spectrum in between sort of indicates how non-compact. It depends only on the group gamma. And if gamma is a free group, then the VCD is 1. Okay, so that's one reason, which I said earlier, that Margulis spacetimes cannot ever be compact because they come from free group actions, and the VCD of a free group is 1. So these higher Margulis spacetimes in dimension D, they're just examples of complete affine manifolds, which all have VCD 1. They're as far from being counterexamples to the Auslander conjecture as they could be. Okay, so that suggests the problem. Let's try to make complete affine manifolds with non-virtually solvable fundamental group and with VCD as large as possible. Okay. We know how to do 1 from Margulis in the subsequent work. 2 comes after 1. Can anyone think of a group, an interesting non-virtually solvable group with VCD equal to 2? Daniel probably has an idea. Do you know? Yeah, surface group, fundamental group of a closed, let's say, a surface of negative Euler characteristic. Okay, let's do that. All right, so let's take S, a closed orientable surface of genus at least 2. The VCD of its fundamental group is 2, and let's study all affine actions of pi1 of S on some R to the D. Okay, so what do we know about this space of homomorphisms here? Well, the work of Hitchin, there's essentially 3 or 6, depending on the parity of D, connected components. So there's not that many connected components. That's good. And there is one component which is super nice, called a Hitchin component. And it has many nice properties. In particular, all the representations in this component are discrete and faithful. That's good, because we want the group to act properly. We at least need the representation to be faithful and discrete. That doesn't guarantee the action will be proper, but it at least gives us a chance. Okay, so let's study the Hitch component. That seems like a good place to look. So the theorem is, and this goes back to Mess, Goldman, and Margulis, and Laborie in some earlier cases, and then in full generality to myself and Tengren Zhang. But if you take an affine action coming from the Hitchin component, then the action cannot be properly discontinuous. So this most promising component with all these discrete and faithful representations yields no proper affine actions of a surface group at all. Okay. So I don't have a whole lot more time. Let me just say a few things about this theorem. Okay, so how many of you know about Hitchin representation? Some of you here probably do. Okay, not that many. So let me say something very vague. The Hitchin component, we know more than just discrete and faithfulness of the representations there, but we actually know a strong dynamical condition called a Nosovness. And for better or for worse, that strong dynamical condition is observed only at infinity, at the sort of visual boundary of affine space, if you like. Proper discontinuity, on the other hand, that's another strong dynamical condition, but that's about what's happening inside of the space, right? And it turns out that the condition for proper discontinuity is not really seen at infinity at all. So we've got this strong dynamical condition at infinity. Proper discontinuity is a strong dynamical condition in the interior, and they don't really interact, but morally they seem incompatible. So the strategy is to do with what I call a geometric transition argument. Here, the key case is not just any Zariski closure, but the case where the flat affine manifold is secretly a flat pseudo-Riemannian structure of signature n(n-1). And the idea is just take that flat pseudo-Riemannian structure and deform it into negative curvature. So you deform it to a pseudo-Riemannian hyperbolic structure. And when you do that, these two strong dynamical conditions that don't interact are forced to interact with one another, and you can derive a contradiction. A contradiction to the existence of such negatively curved manifolds, and then you can kind of take a limit backwards and get a contradiction to begin. Okay, so that's I know that was super vague and probably no one understood what I was talking about there, but just the tagline is deforming into different geometries is sometimes a very powerful idea. Okay, finally, Laura, how long am I supposed to go? Three? Okay. All right, let me state one last. Oh yeah, okay. Well, of course, you should ask. Fine, but you thought this was the right component to look in. You're clearly wrong. What about other components? And the other components are generally worse to look at. We don't know very much about them, but in fact, we did find a way to make some proper actions of a surface group. So I'll spend the last slide telling you about something about that and something actually much more general than that. We actually showed that any right-angled Coxeter group admits a proper affine action in some affine space RD. Okay, so I don't have time to say much about this, but right-angled Coxeter groups are class of groups that are very simple to define, but they have a really deep and beautiful structure theory. I think in this department there are geometric group theorists that know a whole lot more about this than I do. But these are actually quite interesting groups. And in particular, they have a lot of interesting subgroups. So as a whatever they are, as a corollary, we get the existence of a complete affine manifold M, which is homotopy equivalent to a closed surface. So that's VCD2, a closed hyperbolic surface. Homotopy equivalent to any closed hyperbolic free manifold. That's VCD3, that uses Hegel's virtual specialness theorem. And more generally, we get complete affine manifolds whose fundamental group is word hyperbolic with VCD as large as you want. Okay, so we can go beyond cohomological dimension 1. We can actually make the cohomological dimension as high as you want. And you might say, oh, good, you're getting close to finding a counterexample. But of course, the caveat is, to do that, we need to make the dimension of the affine space really, really big, right? So if you look at the little parenthetical remark here, the dimension of the affine space where we make these Coxeter groups act is k choose 2, where k is the number of generators. That's growing quadratically in k, and sort of trivially, the VCD of a right-angled Coxeter group is bounded by the number of generators k. So these are, in the best case scenario, these are complete affine manifolds whose fundamental group has dimension like square root of the dimension of the manifold or something. It's like not close to being compact. We're not getting closer to being co-compact. Okay. I don't have time to say anything about this. I'm sorry. I wanted to show you how to do this. This is something I can show you how to do in a very concrete way. These are very concrete examples. I'll just wave my hands vaguely and say, okay, here's an example of a right-angled Coxeter group. So you know what it is. It's a group generated by finitely many involutions. And then you throw in some more relations saying some of the generators commute. You get to choose which pairs of generators commute. Okay. This right-angled Coxeter group acts as a reflection group in the hyperbolic plane. And it actually acts as a reflection group in the hyperbolic plane in many different ways. And the way we get affine actions out of such a deformation space is there's a trick. You take one action on the hyperbolic plane, you take an infinitesimal deformation of it. That turns out to give you an affine action in R3. And if that deformation contracts the hyperbolic geometry in a sufficient sense, then the action will be proper. So I wanted to show you that more concretely, but let me just get to the general case here. So sorry, skipping this. In general, so some of you probably know that story about right-angled Coxeter groups in the hyperbolic plane. In general, an arbitrary right-angled Coxeter group does not act on the hyperbolic plane as a reflection group, but it does admit some representation into POPQ. So it actually does act in a suitable sense as a reflection group in pseudo-Riemannian hyperbolic geometry for some signature PQ-1. And in fact, there's cool deformations, a lot of deformations of such actions. This is a picture of one. This is a right-angled hexagon group acting in H21, which is anti-de Sitter 3 space. And by studying the deformations of these things, it turns out you can produce proper affine actions. And if anybody wants to know more about how to do that, I'd be happy to tell you, but I'll stop here. But tomorrow I'm going to talk about something different. So yeah. Do you want to go first? Yeah. 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 And you can object to that notion of how it's compact. You could give me a different one if you want. That's not like a kind of like heuristic. They're compact two-dimensional surfaces, but I'm letting that group act on a higher dimensional affine space.
Oh, and then we by that.
Yeah, so if I take a surface group and let it act on R7 or something, right? The action is not going to be co-compact, right?
Okay.
It's going to be some 7-dimensional manifold that maybe you could hope deformation retracts onto a surface or something. It's a 7-dimensional manifold, which is homotopy equivalent to a compact 2-dimensional surface, but the manifold itself is still 7-dimensional. Okay?
Okay.
Yeah. Yes. Yeah.
But then when you're talking about the compactness, you're talking about the manifold, which is explosion, like that higher space, right?
Yes.
Okay.
That's right. That's right. Yeah. That's right. Yeah. The group, the group is the fundamental group of this affine manifold that we made, but it also acts in a compact way on something else, and that's the thing that you use to decide what the dimension, the like intrinsic dimension of the group is. Yeah. Steve, do you have?
Is there any approach that uses dynamics? I mean, when you talked about the deformation from affinity to local, that's some sort of dynamical deformation.
Yeah.
But is
Yeah.
there a serious way to attack it?
Yeah, so I brushed all the dynamics under the rug for this talk, which I think was maybe a mistake because the theme of the conference is dynamics. But somehow Margulis's original examples, like he took like 2 affine transformations and just studied, like directly somehow determined the dynamics of the action. He showed that the action was proper by what's now called the dynamical argument. And other people have generalized that argument to other settings. So that's maybe the first entrance of dynamics. Then, in dimension 3, and there's a generalization in for higher Margulis spacetimes, deciding whether an action is proper. It's of course a dynamical question, and there's I think one of the most beautiful ideas that's come out of this subject is from Goldman, Labrie, Margulis. You take, okay, so you start with a discrete subgroup of SO21 corresponding to a hyperbolic surface. So that's a subgroup of SO21 in particular, it acts on R3 linearly. You then add some translational parts to make it an affine action. You want to know, is that proper? Well, what you do is that's a question about a discrete group action. You translate that to a question about the dynamics of a flow on an associated bundle. So there's this cool thing that I think goes back to Margulis. It's kind of prevalent now that if you want to know if the action of a group on a discrete group on a space is proper, well, you can also sort of make the space bigger. You can take a bundle over that space so that the action becomes automatically proper, and then study geodesic flow on that bundle. And if geodesic flow on that bundle is proper, then the original action was proper. So there's all sorts of good dynamical ideas going into this, which maybe I should have tried to include into this talk, but I didn't. Yeah. But yeah, and to your question, the approach that we took about you're referring to this Anasav representations point of view, is all about the dynamics of how a surface group acts on a homogeneous space. So those are new tools that weren't around when Margulis first started thinking about these things. So we're now using those tools to get more dynamical information about these actions.
But at that point, do you just need an Auslander here, or do you need something more about it?
No, we really need Hitchin here. I don't know. Our argument really needs Hitchin. It's a bit delicate. Yeah. Positivity is a big tool here.
Yeah, that was a great talk and great question.